Welcome back to Feedback Control Systems. This is Module 4.4. We're going to look at pole and zero impact. So the objectives of this module are to review our underdamped system pole plot in the S-plane. Then we're going to do a S-plane to time domain mapping and show you where poles might appear on the S-plane and how they may map into the time domain response. Then we'll look at pole migration impact on the response in the time domain. What happens if we add additional poles to the response? And then finally, we're going to look at the impact of adding zeros into our system and what impact that would have on the response. So first, I want to look at our system pole plot in the S-plane. And a quick reminder, the S-plane, we have a real part we're going to denote as sigma, and then the imaginary part we're going to use as our j omega axis. So what I'm showing here are two poles. They are complex conjugates, as shown here. And you'll see there's a real part and imaginary part. So from a previous module, we explained how to find those poles. They both have the same real part, negative the damping times the natural frequency. That's the real part. It's the same for both. And for the imaginary part, we have either plus or minus j, and then the same part here, the natural frequency times the square root of 1 minus the damping factor, damping ratio squared. So that is the representation of them, but I want to dig in a little bit further here, and as we start to interpret this S-plane in the pole locations, show you how that relates to the previous module when we talk about things like overshoot and the peak time and settling time and things like that. So the first thing I want to do is say, if from the origin here, I were to draw a straight line to a pole, and I'm just going to take the upper one right here, I'll draw a straight line. Now notice here, I define that as omega n. Well, I want to quickly work with you to solve that. Notice I have a triangle here that is represented. Okay, and I know this length right here, my x variable here. Okay, I know my y variable right here, right? And I can solve for what? The hypotenuse using what? I can use the Pythagorean theorem. So first, let's just state what is the Pythagorean theorem. We basically have a squared plus b squared equals c squared. So that's our Pythagorean theorem, where the c is the hypotenuse, and a and b would be basically the x and y variables that I showed below. So for our a variable, we said we have negative zeta omega n. That's our a variable, if you will. Our b variable we said is our y variable. So again, I'm just going to take the top one here, and that's going to be, we know we're on the j omega axis, so I'm going to ignore the j, but the magnitude, the length up of that is going to be the following. I have omega n times the square root 1 minus zeta squared. That quantity is going to be squared, and then that's going to be equal to c squared, which again is the hypotenuse. That's what I'm solving for. So when I work this out, I'll go down and I'll say I have relative to this term right here, I'm going to have my zeta omega n, essentially getting rid of the negative sign. I'm going to leave that as shown here. And then when I square this, notice what I have over here. I have my omega n squared, and then this term right here, let me change this for brackets. Now when I have this term right here, I'm going to be left with 1 minus zeta squared. Okay? Because this square will get rid of the square root sign, so that square basically just comes, and I have that term right there, and that's going to be equal to my c squared. Now what I can do is leave this term the same. So I have my zeta omega n squared plus, now what I'm going to do is distribute this in, so I'm going to be left with my omega n squared times 1, and then I'm going to have my minus omega n squared zeta squared, so I'm just going to combine those omega n zeta squared, and then that's equal to c squared. Now what I can do is say, well, I have a zeta omega n squared and a zeta omega n squared with a negative sign, so that term and that term cancel, and what I'm left with here is c squared equals omega n squared, which then leads to the result that I have c equals omega n, which would be my hypotenuse, which is what I show here on the graph. I have my hypotenuse. So the length from the origin to that pole is the natural frequency. Now, I introduce a second term here called the angle. So the angle is that line going from the origin to the pole, that angle relative to the real axis. What is this angle? And we're going to call that theta. Now, how do I find theta from below? Well, we know from math again that that angle is the cosine of the adjacent, which in this case is the x-axis. So let's write that down. What is theta? Cosine of theta. It is the adjacent term, which is our the distance here of negative zeta over omega n. That's our term. And then it's divided by the hypotenuse, which is omega n. Okay? So if I look at these, the omega n's canceled, and I have my cosine of theta equals negative of the damping ratio. But if you look down below, you'll see that I basically have I don't have the negative sign. Now the reason of that is because cosine being the even function, it doesn't matter. So essentially what I'm doing is getting rid of the negative sign associated with that. So an interesting fact here is if I want to know the omega n from the pole locations, the natural frequency is just the distance from the origin to that complex conjugate pole. And if I want to find the damping, all I need to do is take that angle, theta, take the cosine of that angle, and that will tell me what the damping ratio is. So as a quick test, remember from previous modules, if that angle theta was 0, so those two poles, those complex conjugate poles, were to both be the same. Two poles at the same location, what happened to the damping? That would be a damping of 1. Cosine of 0, that angle now becomes 0. Cosine of 0 is 1, so that works. Now the other case is what if those two poles were on the j omega axis? In that case, our angle is at 90 degrees. Cosine of 90 is 0. We have no damping. We have an oscillator response. So that should give you those two end cases, and then anything in between. Hopefully you can see that ratio of the damping ratio relative to that angle. So that is that information that I wanted to show on this slide. So by knowing the pole locations, you really can find graphically the damping ratio, the natural frequency, and then from the previous module, you can find a whole host of other things like the overshoot, settling time, etc. So now I'd like to look a little bit more at this S-plane and show some mapping that we have into the time domain. So one thing we're going to do is the following. If I have poles anywhere on this line, this black line, if I have poles anywhere on this line that I'm showing here, that percent overshoot is going to be the same. Now, how can I say that? Well, remember, because all of the angles here, that angle is the same as that angle, etc. These all have the same angle, theta. And remember, cosine of theta is what? The damping. We have the same damping, we have the same percent overshoot. So if I want to change the percent overshoot, if I want more overshoot, so that would be more overshoot. Now notice now that angle theta is now increasing. So my cosine of that angle, the damping would now be decreasing. With a decreasing damping ratio, I have now more overshoot. So that's one thing to see is I have, as my poles move along this move along this black line here, I will have percent overshoot being the same. Next, what I want to do is look at the peak time here. That's the time where the overshoot occurs, the peak overshoot occurs. Now notice for my peak time, I have two lines that are horizontal, here and then here. So if I have poles on any of these lines right here, that will have the same peak time relative to when the overshoot occurs. Or if I want that peak time to be less, then I would move any of the poles along this axis right here. So again, similar to the percent overshoot, as long as I follow that line, if I were to put a pole anywhere on those lines, I would have the same peak time. And then similarly for the settling time, notice I have now, instead of horizontal, I have vertical lines. So if I put my poles on anywhere on these vertical lines going up and down, I would achieve the same settling time. So I want to now merge and actually show this graphically and show the impact of that pole migration on the response. So this case right here, notice we had the horizontal lines, which was the previous case we had. So for the vertical lines, I have the same settling time. So that's what I have here. So in this case, the settling time is the same. Settling time is going to be the same. And if I look at the three cases, first I have poles that are closer to my real axis, and then they slowly go away. Well, if I look at my three responses here, they all sort of settle out at the same time. They have different overshoots, right? Different overshoots because why? Angle of 1 is theta 1, theta 2, theta 3. So the angle's growing, so my overshoot is growing. It's the most for case 3, the least for case 1, but they all settle out at the same time. Okay, so that's one important thing to know. Now we see these two cases for the, this was the peak time. Okay, this was the peak time along these horizontal trajectories here. And so notice if I have a pole at location 1, I get maybe more overshoot. Why? Because my angle theta, right? My angle theta here is bigger than it is for theta 2. So I have more overshoot as my angle gets bigger, more overshoot. But because they're on the same line, that peak time, T sub P, is similar. It's the same. Okay, and you can see that, and I could add even more poles along that trajectory to see that. And again, depending on where my 2% settling time is, I would have my settling time there for all three of those cases. And then finally, at the lower graph, again, I have noticed the angle here for all these are the same. So my damping's the same, meaning I have the same overshoot for all three of these cases. However, if I look, relative to point 1, 2 is higher than 1, right? 2 is higher than 1, so I would get more overshoot. And 2 is to the left of 1. So again, let's reset on that. Sorry, I think I made a mistake. So they all have the same settling time, but if you were to compare 1 versus 2, 2 is higher than 1 and 2 is to the left of 1. So you can also see it relative to 2 is to the left of 1 here and 2 is higher to 1 here. So you could actually look at those responses and see how that plays out. But the key is that they are the same overshoot. Some may have a peak time that is faster than the other one here, and also the settling time may be slower or faster depending on that. So this is very important as you're starting to look at your design. Where, based on the modeling of the system, are your pole locations? And then if you want to build a controller such that the natural response of the system wants to do this, and if you want the response to actually do something better, quicker, faster, whatever, you can now, through your controller, design where these poles might want to be and maybe impact that system response. So this will be a very important slide to kind of go back and forth between this slide and this slide to really get that feel and understanding as you're doing some design work later on in the course. Now, what happens if I add an additional pole to a second order response? So let's say I have my underdamped case and I have my two poles, my complex conjugate poles P1 and P2, and they're all going to be the same for all three cases that I'm going to look at. I'm going to look at three different cases here. But what's going to be different in these cases is the following. I have my pole 3. First, it's kind of close relative to the real axis. It's kind of close to the complex conjugate pair, the real part of those. And then what happens is P3 sort of migrates farther to the left. And for this example, it's so far to the left, I can't even see it on my graph because it's so far to the left. So first, when I have this case, case 1, notice what happens. So what I'm going to first do is look at essentially first and second order response of these cases here. So when I have a single pole, right, that would give me essentially this exponential response as I'm showing here. So for case 1, I have some sort of like exponential response associated with that. However, as P3 moves to the left, notice that response gets faster and faster to the point where I'm at case 3. I don't even show it on this plot because it's happening so much faster relative to the dynamics of the second order system. I can essentially ignore or neglect that. And that's what this node is saying right here. If the value of alpha, which is the pole location for pole 3, if that value of alpha is much, much greater than the product of damping ratio times omega n, which is, again, the real part of our complex conjugate pole, if alpha is much, much greater than delta omega n, then we can basically ignore that pole. The dynamics of that first order pole happen so much faster relative to the complex conjugate pair, we just don't need to include it. And you'll see that here in the case 3, where essentially it looks like our regular second order response as I'm showing here. Okay? But in case 1 or case 2, look what happens. Case 2, yeah, it's kind of far away. That second order response more or less dominates. But look, I have a little bit for case 1 and case 2. A little bit, I'm not actually starting here at 0. I'm actually starting at a little bit higher points. So case 1, when P3 is much closer, I actually start way up here, and then it kind of goes down, and then it kind of matches up. And that's basically because of the two responses coming together here and adding together. So this will be very important as we add additional poles, maybe through our controllers in our system. We have to be very sensitive to where we place them in terms of how it impacts the response. Okay? So that'll be more, I think, important and relevant when we look at design cases. Now I'd like to look at some of the impact of zeros on the response. Now, even taking another step back, let's just remind ourselves where poles and zeros are relative to our transfer function. Poles are going to be in the numerator. Zeros are going to be in the numerator, poles are going to be in the denominator. So really we're looking at things so far in the denominator relative to the poles. Zeros now, if we add some zeros in the numerator, what does that impact on the system? Well, what you see here in red, zeros really don't affect the nature, the damping of the time response, but only what? Only the amplitude of it. So if we add, basically, first of all, we have a system with no zero. That's this farmost blue plot right here. You can see, okay, that's our system. But now if we start adding a zero, notice based on the location of the zero, the settling time, looks like it's about the same. The peak time, it's close. It's essentially the same. Slight deviation, slight differences. The overshoot, again, there is a slight difference, certainly. Here it may be 30%, here it may be 50%. So there is a slight difference. But at a high level, it's not drastically changing the response. So again, maybe the amplitude a little bit, so there is a little bit of that overshoot impact that we see, but again, not a driving factor as we add zeros in our system. Certainly not for when the system sort of settles out. So that's going to be important as we look at placing zeros in our system. And again, more on that when we get to the design and building controllers. Now, one specific case of zeros is what if we add a right half plane 0. So on the previous slide, notice all these zeros were negative. These were all left half plane zeros. But what if we add a right half plane 0? We know, looking previously in our pole plots, if we have a pole in the right half plane, the response will grow and become unstable. But can we put a 0 in the right half plane? The answer is yes, you actually can. But a very interesting thing happens. Whereas in the previous slide, look, they all start at 0. They all sort of go upwards trend. When I add a 0 in the right half plane, look what happens. It actually starts by going in the opposite direction. It actually starts by going negative. Now, in control jargon, this is referred to as a non-minimum phase system. But in practical terms, we see this a lot in certain systems, is you actually have the response, you want it to go up, it actually starts by going negative, and then it eventually will go up. In some power conversion systems that we model, we see this a lot of times. So one case you might see this in is what we call a DC to DC converter that does a boost function. So what happens is if you do a step change, first of all, you'll say, hey, I want to go higher in voltage. Sometimes it'll actually go a little bit negative, and then it will eventually recover. So we do see these in certain instances, and so if you see that response dip in the opposite direction first before recovering, good chances you have a right half plane 0. Now, as we talk about adding poles and zeros, what we're doing is we're slowly walking you to the position of controlled design. How do I build a controller to get a system to do what I want, that has the overshoot that I want, the settling time that I want, basically the response characteristics that I desire for my application. Now, part of this is, hey, if I add a 0 and it can potentially cancel out a pole, what happens? Well, it actually can get to a system where, hey, if I have a third order system and if I add a 0 and make it a second order system, if I can truly cancel a pole, that might have some desirable characteristics for what I'm looking to get in my application. So there are some rules here. Now, obviously, as we model a system, how good is your model? How good do we know the location of one of these poles that we're trying to cancel? And so there's some guidance down here. If the 0 in this case, pole 3, they're approximately equal, and we'll show you some worked examples where we'll say what is good enough, what is approximately good enough to make this happen. So technically what happens is the residue, and you can see the definition, the residue is the numerator of when we do our partial fraction expansion. But if the residue of the exponential decay is much smaller, and again, what is much smaller? We'll kind of define that as we do some worked examples. If the exponential decay is much smaller than the amplitude of the second order response, then we can cancel those. So essentially, as we do looking at partial fraction expansion here of our third order system, and that residue, i.e. the numerator term, is pretty small, meaning it doesn't have much impact on our system response, then we can actually do that pole 0 cancellation and treat it as an approximately as our second order system, looking at our underdamped cases or critically damped cases, etc. So I think this will become more evident when we do some worked examples on that. So this will conclude this module. If you have any questions, by all means, please reach out. Thank you.